Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to Calculus 2 students who are going through and learning about substitution involving trig functions. So you are asked to integrate something like this, which is a definite integral from negative pi to positive pi of sine of some angle, which that angle is defined by mx, times the cosine of a completely different angle. Why don't you take a moment, try to figure this out, and when you come back, we'll go through it. The first thing you should probably be attracted to here is the fact that you have a symmetric interval from negative pi to positive pi. Generally speaking, with trig functions, that means that you can use some type of symmetry, and that's probably what we're going to use here. To perform this integration, it's probably going to be a good idea to recall a very obscure set of theorems from trigonometry. I'll go ahead and write them off to the right-hand side here. And here we have it. This is the product to sum formula. The sine of A times the cosine of B is equal to 1/2 the sum of the sine of the difference of the angles plus the sine of the sum of the angles. Now, something to note here is that this theorem is really not a memorizable theorem. That's what I tell my students. Instead, I tell them that it's a good idea to remember that this theorem exists so that when you're dealing with a product of trig functions that have different angular speeds, in this case, the angular speed here is mx, or technically m, and the angular speed there is n. They have different angular speeds, so therefore you should just immediately think, oh, I have a theorem that I can combine these two into a sum of trig functions. And in this case, we can sum of the sines and half of that value. So let's go ahead and use that here. Now we get down to this point, notice it does actually match the theorem we wrote down. And we'll go ahead and do some factoring. There we go. Let's go ahead now and just integrate each of these terms separately. Again, the point of this problem is really to showcase that you need to use the product of sum formulas every once in a while when you're working in mathematics, actually. And it's just good to know that they exist. Not to remember them, but just to know they exist. Now, before I begin going through and evaluating this, you should pause. I try to tell my students this, just pause every once in a while before you go rushing through a problem and think about the problem that you're facing. Remember, m and n are integers. They could be the same number, they might be different numbers. It doesn't really matter. What matters is that you know from trigonometry what the coefficient of x is really telling you. That coefficient, sine of m minus nx or sine of m plus n, x, doesn't really matter which one you're talking about, just tells you how many cycles that the sine function goes through between time 0 and time 2 pi. For example, if you were looking at sine of 2x, then you know that between time 0 and time 2 pi, the sine curve goes through 2 full cycles. And if you think about that, that just means that the area underneath the curve, so you have some signed area here, that should be the same as that area there, but the area underneath the curve should be the opposite, right? And they should cancel out. So if I were to integrate sine of 2x from 0 to 2 pi, it should be 0, geometrically speaking. If you were to change the value of the argument for sine to be something like, oh, I don't know, let's say sine of 2.5x, that means that between 0 and 2 pi, those time values, it should go through 2.5 cycles. Here's the first end of the first cycle, here's the end of the second cycle, and here's halfway through the third cycle. And in that case, the areas do not cancel beautifully, right? This area is the same as this area, is supposed to be the same as that area, and these are the opposite areas. Notice there that all the areas do not cancel out. The first 4 areas do, but the third area is still there. So if it's a non-integer value, then it might be the case that areas don't cancel out. And in fact, it will not be the case that they cancel out, at least between 0 and 2 pi. But the question that we're being tasked with here is to find the area underneath these curves between negative pi and positive pi. If you know your trig functions and their graphs, then you know that the area between negative 2 pi and positive 2 pi is symmetric underneath the curve. And in fact, if you only wanted to go from, let's say, negative whatever this number is to its positive version, and you want to find those areas, you will find that the area on the negative side, from, let's just call this negative b to positive b, the area that I'm shading in red here is going to be equal and opposite to the area I'm shading in green there, and they will cancel out. And that's actually the trick to this problem. There's no need to actually run an integral or do the calculus. I tend to try to tell my students that when you're doing calculus, you should always do arithmetic before algebra, algebra before trig, trig before pre-calculus, and then pre-calculus before calculus. In this case, I'm just showcasing a little bit of my trig knowledge to really understand that the areas will cancel over symmetric intervals for the sine curve, and specifically for an unshifted sine curve. And if you take a look at these two sine functions, they are not shifted. In other words, they're not something like sine of m minus n x plus c. That plus c would cause a shift horizontally, and that's not what's happening in either of these two cases. So these are unshifted sine functions. One goes faster than the other, but it doesn't really matter actually which one goes faster than the other or anything like that, because you could break this integral up into two sub-integrals using properties of integrals. And now you can really focus on each of these two problems separately. This guy right here is just a sine curve, an unshifted sine curve over a symmetric interval. And because that interval is symmetric and the way the sine curve looks, I happen to know the area underneath that curve from negative pi to pi, everything will cancel and that will be 0. I don't need to do any calculus there. The same thing is true for the second integral. So this problem really is all about recognizing the shape of the object that you're working with, or the shape of the functions that you're working with. Well, technically it's not just all about that. It's also about knowing when you can actually invoke a theorem from trigonometry. Obscure as it may be, we know it exists and we go ahead and use it. And the use of that theorem allows us to then zero out the area, or say the area underneath those curves is 0.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.